Thank you, Mr. Chairman. Assalamualaikum and good afternoon, everyone. Okay, I'll be talking on the Asian rare earth experience. This is a sensitive subject. And related research activities by Nuclear Malaysia. What we have done all these years in this particular area. Okay, the outline of my presentation is first I'm going to look at the ARE, the Asian rare earth, chronology of events from establishment to closure. Then, what is the ARE process and its radioactive waste? Next, I will look into the closure of the Asian rare earth. Is it about safety or economics? Follow on, I will be talking on the Asian rare earth after its closure, how the DND work, the decontamination and decommissioning works is done. And on my next part of this talk, I will talk on the R&D in rare earth and norm at Nuclear Malaysia. There are 4 projects that will highlight. First is the treatment of radioactive debris. This is the organic waste from the Asian rare earth plant, which is used for the separation of the light and heavy rare earth that have been contaminated with radioactivity. How to solve this problem? Next, I will show you what we had developed or carried out in terms of the hydrometallurgy process for xenotime. This is a local mineral that has very high content of yttrium. It has 60% of yttrium and more than 8% of dysprosium. So as what our first speaker, Jack Litton, had said, that these 2 elements are the future strategic elements for rare earth. And we have it in Malaysia. So it's just like another gold deposit for Malaysia. How to get the gold out of this mineral. And then I will look into, or I will show you how we did research in removal of non-contaminated minerals, where these contaminated minerals are removed from their radioactivity elements. And finally, I will show you in terms of the work done, if you have a non-waste. In particular, I will show you our oil sludge waste from the oil and gas industry, which is radioactive, and we do a dilution and vitrification method to reduce the level of radioactivity, as well as to make the material, the radionuclides, non-leachable, cannot get out from the waste form. Okay, so I start with the Asian rare earth. So the ARE establishment and objective. The ARE was incorporated in 23rd November 1979. It's a joint venture company between Japanese, that is the Mitsubishi Chemicals, and a Malaysian partner, Bay Minerals Tabung Haji, and individual investors. And the purpose or objective of ARE is to recover rare earth compound from local monazite minerals. Okay, next we go into the operating license. ARE started its operation, that is in April 1982, at the 7.2 kilometer Jalan Lahat in Bukit Merah Industrial Estate. This is a place somewhere in the central of Peninsular Malaysia, and the initial license was issued by the Health Ministry. Then, following the formation of the Atomic Energy Licensing Board, in 8 November 1985, the ALB ordered a stop operation for the ARE because the company operates without a license. And on 16 January 1987, ALB issued a Class A license to ARE to resume its operation. So now we look into what ARE is doing. ARE process our local monazite by a method called caustic soda cracking method. And in this method, the monazite is first digested by caustic soda or sodium hydroxide, and upon the solid and liquid separation, the liquid will be formed into trisodium phosphate. This is a fertilizer byproduct from the mineral. The solid will undergo acid digestion process where another solid liquid separation will remove the thorium waste from the liquid rare earth. The liquid rare earth will then undergo a separation process by multi-stage solvent extraction. Here, they are using the diethyl hexyl phosphoric acid or DEPA to produce two products, the light rare earth carbonate and the heavy rare earth carbonates. So if we were to look at the rare earth chain of ARE, you can see that ARE got its feed material, the monazite, from our local among plants. And the monazite are sent to ARE for the caustic soda cracking process, and from it we get the mixed light and heavy rare earth. These radioactive free products will then be exported and sent, for example, to Japan and Europe for export. And here, in these countries, the mixed rare earth will be separated and purified into individual rare earth elements. So these rare earth elements will then be turned into either its oxide or metal for their high-tech and green-tech products. So now, with the ARE, that's the radioactive waste, the thorium waste. And this had led to the public protest. So in 1984, residents of Papan and nearby towns signed a protest letter and sent it to the Prime Minister, Perak Menteri Besar, the Minister of Health, as well as the Minister of Science, Technology and Environment to protest the presence of ARE. In 1986, representatives from 7 areas nearby the plant formed a committee called the Perak Anti-Radioactive Committee, or PARC. And the following year, about 10,000 people participated in a rally condemning the ARE for its operation. Now, what is the radioactive waste or the thorium waste? I did an analysis on this particular waste. You can see that, and I compared it with similar waste from Brazil and India. You can see that in terms of the thorium content, it's a bit lower than what is being produced in Brazil and India. And we have almost similar uranium content in our thorium waste, but a major difference is that the unrecovered rare earth is higher in our thorium waste. And if you look at the pictures here, this is the long-term storage facility at Bukit Keledang, where the thorium wastes are stored in steel drums and put inside this facility. So in 1985, the government decided to relocate all the waste that is produced from the plant to the ARE or to the Keledang range, and the Keledang range or the LTSF was completed in 1989. Now we refer that there are some court cases filed by the residents on the safety aspect of the ARE. And in February 1985, residents of Bukit Merah sued the ARE, claiming its operation endangered their life, and the case was heard at the Ipoh High Court. Then, on 11 July 1992, the Ipoh High Court issued order for the ARE to stop this operation and transfer all waste to the LTSF. Another decision was made on the 23rd December 1993. This is by the Supreme Court, which overturned the High Court decision on two grounds. The court was of the opinion that ARE's experts were more believable in terms of the result of the test conducted by them, showing that radiation was within permissible level. Secondly, the Supreme Court said that the residents should have gone back to the ALB to ask that it revokes ARE's license, because ALB has the power to do so under the Atomic Energy Licensing Act. So maybe you could ask Professor Sulaiman and Dato' Raja Aziz about this. Now, in 14 January 1994, the ARE made an announcement that it wants to close its facilities. And it cites the main reason for that is the low price of rare earth. So if we were to see, this is from Geoscience Australia. In processing of the rare earth, we have the initial stage is what is known as the monazite placer period, where mainly monazites are used as the feed material. But somewhere in the early 1960s, we have the mountain pass period, see, where the feed materials come from Molycorp in USA, and these were followed by also feed materials from the monazite. But somewhere in the middle of 1980s, the China factor comes in, where we have a lot of supply of rare earth from China, and this is called the transitional period. And this, at this particular period, that the ARE operates. And at this period too, there was a low price for rare earth, and this makes the operation of ARE to be not economic. Now, if you look at the market price for mixed rare earth, for monazite, you can see that in 1996, the price is 0.28. 1998, it was increased to 0.4 US cent per kilogram. But for the mixed rare earth, it decreases from 2.6 US dollar to just 1.19 US dollar per kilogram. But for the high purity rare earth, it still can maintain, because even though for sample cerium, it's just a small difference. And for neodymium, there's an increase in the price of this high purity rare earth element. So it's also the yttrium. Now, if we were to look at how is the production cost at our ARE, so these are the itemized activities that are costing ARE, its operational cost, and the total X work for ARE is about 4.25 US dollars per kilogram. So this price is much higher than the price of the light rare earth that it produces. So that's why it cannot compete and cannot go on operating the plant. Now, when the ARE closes down, so it needs to do the decontamination and decommission of the ARE plant site. So this involves demolish building at the plant site and the waste water treatment site, excavation and removal of contaminated soil at the plant sites as well as the wastewater site, and then transportation of materials and placement into the engineering cell located at the Bukit Keledang. Then it got to restore the plant site by backfill the plant with clean soil. And then finally it should release the site for other industrial activity. All this work was completed in the year 2006. So we can see that there are two different cells. First is the engineered cell. This comes from the plant site, and this is another cell, the thorium cell. This is from the thorium and contaminated material from the LTSF facilities. So they are using the engineered layer where the waste will not be seeping through the ground. And some of the pictures for when they're building up the engineered cell, demolishing and stockpiling of plant site materials before transportation. This is the transportation of the contaminated materials. And then we have in February 2005, progress of excavation and backfill of the plant site. This is also another picture, but in June 2005, you can see that all the soils have been removed and replaced with clean soil. And this is a progress in February 2005 on the engineered cell at Bukit Keledang. Another picture in June 2005, and this is how it ends up. A completed engineered cell near the LTSF facilities at Bukit Keledang. Now, the next D&D works involve the long-term storage facility. So these involve activities in demolish the LTSF building, dispose of the debris and the thorium hydroxide and contaminated materials into engineered cell 2 or thorium cell. And this engineered cell 2 will be constructed adjacent to engineered cell 1 in Bukit Keledang. And at present, they are still working on it where the waste is conditioned and it will be disposed there. So this is the proposed design and some of the pictures on the engineered cell 2. Okay, the demolishing of the long-term storage facility. So that is on ARE. So my next presentation will be on the R&D in rare earth and non-materials at my agency, that is the Malaysian Nuclear Agency. Okay, during the ARE process, they are separating the light and the heavy rare earth by using a multi-stage solvent extraction. And the chemicals that they use is called the diethyl hexyl phosphoric acid. And this diethyl hexyl phosphoric acid contains 30% kerosene. So when the ARE was closed in 1994, it was found out that this DEPA was radioactive contaminated. So it can't, because it's in organic liquid phase, it cannot be put into the disposal cell. It needs to be transformed into a solid form. Then only you can dispose it. So if we look at methods that is used in transforming liquid organic to solid waste form, there are actually 4 methods that have been used. The first is you mix and blend it in polymers. Then you can also mix and blend it in urea or formaldehyde. Another material that is used is that it is mixed and blended in apatite mineral. We at Nuclear Malaysia had worked with the Australian Nuclear Science and Technology Organization, and we actually had come out with a cement wasteform. But it seems that this wasteform is not that stable for means of long-term disposal. So we then, through research, come out with a different method. So this is a method that we use where first we remove the kerosene content in the depot, and then the first stage is to form a gel form from the liquid organic, and next this gel form will be converted into a semi-solid form, and finally the final stage is a solid apatite waste form that is produced. And some special features of these waste forms is that it transforms organic to solid waste form for easy waste management. Then there's a strong bonding of the radioactive material to the apatite. Next, it has a low solubility of apatite waste form. That means the radioactive nuclides will be kept in the waste form for a long time. And we can also recover the kerosene as a byproduct from this process. And finally, we are able to produce a waste form that is reduced in volume compared with the initial waste. The next research that I want to show to you is how we develop a hydrogen process for our xenotime. As I mentioned earlier, xenotime is unique in that it has more than 60% yttrium content. The formula is YPO4. It's a phosphate group mineral with high yttrium content. And it also has high dysprosium content. And if we were to look at, in terms of the natural radionuclides, you can see that unlike monazite, xenotime has higher uranium compared to thorium. So this is the process that we develop. Involves starting material xenotime, and then we use an alkaline fusion process. After the solid liquid separation, we can get the trisodium phosphate, and then it involves acid dissolution, then selective precipitation, where we can separate the yttrium from the uranium and thorium concentrate. So among the advantages of this process is that you produce a minimum radioactive waste volume. Use of dilute acid for the dissolution process, and recovery of phosphate as byproduct. So this shows from xenotime you get a yttrium oxalate, and from this you get the yttrium oxide, and you can produce byproduct in the form of trisodium phosphate and uranium. The next project that I want to show to you is how we remove the non-materials from Malaysian radioactive contaminated minerals. So, actually, Malaysia, we face a problem that most of our heavy minerals are contaminated with thorium and uranium. So, in 1990, Malaysia lost revenue of 100 million ringgit due to this issue. And because we can't export the minerals, it creates contaminated dumps, which that is hazardous to both public and the environment. So what we have done is we remove the contaminated non-materials. For example, this is for zircon. Initially, can see that zircon has a lot of contaminants in it. After the process, we get a clear zircon. And this can be seen from the color. From dark color initially, you produce a white zircon. And zircon is mainly used as white tiles. So to prove that it can be used in white tiles, you need to do two tests. First, the fire test. That means, can it give the whiteness? And secondly, it should have a glaze test. So we did both, and it seems that after the treatment process, our zircon satisfied both tests, the fire as well as the glaze test. So that means we can upgrade our low quality zircon into high quality or high grade zircon that can be used for both local as well as exported to other countries. We had also developed a different solution, a solution to remove the uranium and thorium from industrial carbide waste. And with this, we can say that we can solve high cost of the leaching chemicals that is used. And finally, we did a research on how to condition the norm waste into something that is more acceptable. And this is what our work is. We look into one of the radioactive waste in Malaysia is the oil slush that is produced, oil slush and scale that is produced from our oil and gas industry. So the natural radioactive element found in this particular waste is the radium. And radium is more soluble compared to either uranium or thorium. So using a very low radioactive material, that is the local red clay, we are able to reduce the radioactivity of this waste to that of background. And from this mixture too, we are making a vitrified layer on the wasteform, and this from our leaching test using the ISO standard 6961, we found that no radionuclide was leached out even after 2 years of leaching. And it has the brick that is produced has a strength, compressed strength of 4 times that of our commercial clay brick. So with that, I end my talk, and I would like to acknowledge the conference organizer for inviting me to present this paper. And also I would like to acknowledge, because actually my colleague Dr. Abdul Wahab should be the person that speaks at this conference, but he can't make it because he's in overseas on another assignment. But Dr. Abdul Wahab provided me all the particulars regarding the chronology of event and also the DND at ARE, because he was then the director of ALD when ARE was in operation. And I also like to acknowledge my thanks to the management of Malaysian Nuclear Agency for supporting me to present this paper. Thank you for your attention.
Thank you for your attention. Can you put our hand together to thank all the 4 speakers?